It was too good to stop you. Okay. So as you can see, we've quickly lost control of the time, but that was too good to stop. So we're going to move right along to Lauren Atlas's presentation on effects of expectation and placebo on pain, a neural circuit perspective. Lauren.
Thank you. So thanks to the organizers for the invitation. This has really been a wonderful meeting so far, so I'm happy to be part of it and looking forward to the conversations we're having. So I'm going to be focusing not on placebo, actually, on pain and aversive learning. So that was a typo in the schedule. And before I get started, I just want to make a disclaimer. I'm here in my personal capacity. This is work I did before I went to the NIH. So any opinions I'm presenting don't represent NCCAH or NIH. Catherine can talk about those. I'm just here in my personal capacity. So although you don't really know which talks are going to come before you and what's going to be said, I think today we're already sort of primed to not think of these circuits as involved in reward. But if we were a New York Times reporter doing a study on undecided voters about Hillary versus Trump, we might, if we saw activation in the striatum and the VMPFC, we might think that those participants are experiencing reward because they really like that candidate. So today we're a little bit already beyond that. But traditionally, these corticostriatal circuits are thought of in terms of value learning very much. People tend to associate them with reward learning. So Tor alluded to this, but in these kinds of studies, they look at the relationship between probabilistic cues, things like, in this case, like you're playing some game, you could have roll different dice combinations, and they look at how these types of cues induce expectations about these potential rewards. So just to be concrete about what that looks like, let's say I'm playing a game, first trial in the game, I roll a 2. I have no idea really what to expect on that. I receive a reward as an outcome. This generates what's called a prediction error, denoted by this delta symbol. That's the difference between my expectation, in this case I didn't know I was going to win a reward, and the actual outcome. And so, and then depending on what's called my learning rate, that'll dictate what I expect the next time I roll a 2 on the dice. So if I have a low learning rate, let's say I'm not paying attention at all, I'll continue to expect nothing when I roll a 2. Versus if I have a high learning rate, I may update my expectation right away and expect to get rewarded the next time that 2 comes out on the dice. So using these types of computational models, people have shown, and Frank also talked about this a bit, that the ventromedial prefrontal cortex is associated with the computation of expected value, while the striatum is supposed to predict these reward prediction errors. And this has been shown in recordings in dopaminergic neurons, and then we see this over and over in human imaging studies. Now, as I said, this is often discussed in the realm of reward tasks, because I think a lot more labs are ready to study reward outcomes. They don't have to deal with all the IRB precautions with pain. But the same signals also underlie learning about pain, which we've heard already going along. So the first really compelling example of this in the human imaging literature was by Ben Seymour. And so he showed that cues that have different probabilities to lead to high pain or low pain predict these type of expected value and prediction error signals in the striatum. And likewise, if you're in a capsaicin model where you have some levels of tonic pain, similar signals can predict both relief and exacerbation of pain. So they had both appetitive prediction errors, meaning when your pain was lessened, and also aversive prediction errors, meaning when the pain was enhanced. And we were really interested, so this is great to see that these signals exist, but one of the questions when pain is ultimately subjective is how do these types of computations and this type of value learning actually influence the ongoing subjective experience of pain? And so that was the goal of our first study, is to understand the relationship between value learning, expectancy, and pain. So in the first part of my talk, I'm going to talk explicitly about expectancy effects on pain, how we looked at this type of learning and effects on subjective pain perception. And then after this, I'll talk about work trying to decompose the different types of expectations, how to look at the relationship between instructions and learning. And finally, if we have time, we'll look at how self-generated expectations shape aversive learning. So expectations are thought to come from 2 main roots. When we think about, a lot of us use the placebo analgesia model to think about how expectations can affect pain outcomes. And so you have both the explicit knowledge and your prior experience or associations that you've learned in the past through experience. So for instance, you have what your physician might tell you about the treatment or what you might read on a jar of pills that you've been prescribed. But you also have all the prior experience with the clinical context and associations with cues, and those also serve to increase your expectations, which in turn can modulate your experience. So what we did when I was a PhD student with TOR was to combine these types of approaches to enhance expectations, measure how they affect responses to noxious stimuli using a thermal pain model, and then look at how that, in turn, those responses drive trial-to-trial subjective pain response. So the paradigm, we gave people verbal instructions that when they heard one tone, low pain would follow, whereas when they heard another, high pain would follow. And then they went into a conditioning phase, so I guess some of the formatting is going to be off, in which each cue was followed by stimuli calibrated to elicit ratings of low pain, 2 on an 8-point scale, or maximum tolerable pain, the level 8 on the 8-point scale. Then, unbeknownst to subjects, we switch into an experimental phase in which each cue is equally likely to be followed by its predicted level or a single level of heat calibrated to elicit ratings of medium pain. So all of our analyses focus on responses in the brain, physiological responses, when the stimulus itself doesn't vary, and the only thing that varies is those cues that preceded it. We measured pain reports and brain responses to heat, and what we find is that pain is reduced by about 20% when the same temperature is preceded by the low pain cue, relative to when it's preceded by the high pain cue. And this is highly consistent across individuals, as well as within individuals over time, and I'll come back to that point. So here is the same paradigm in a number of different contexts. So when we're manipulating attention toward and away from the body, when we're giving an opioid analgesic through an infusion pump, and we see the same effects even in adolescents with and without anxiety disorders. So we get these really robust expectancy effects on the thermal pain model. We then were interested in asking, how do these effects come about? So which brain regions are responding to cues during heat and then leading to these changes in subjective pain? So beyond just the fact that they respond to the cues, does that actually lead to changes in pain? I'm not going to present it, but I'll just note that the NPS that TOR responded to, every single region there, the whole network, shows differences as a function of cue. But when we looked at the subset of regions that formally mediate the relationship between cues and pain, what we found is that we've had significant mediation by responses to heat in the insula, thalamus, and dorsal anterior cingulate. Now, I'm not going to talk about specificity of the responses within these regions, but these are the same portions of the regions that responded to the changes in noxious stimulus intensity. So this showed us that indeed these types of cue-based learning can modulate trial-by-trial responses within the pain responsive regions, and these can give rise to the subtle variations in pain within a person. Now, our second question was about how these come about. So we wanted to test between two hypotheses that have been addressed in the literature. One is that expectations cause changes within sort of control regions that in turn inhibit or regulate the response to pain. So this is consistent with models that sort of think of pain in an emotion regulation framework. So you have some belief and you downregulate pain in a sort of active process. A second hypothesis that I think it seems like we're all sort of converging on here is that expectations change the value of pain in terms of an affective learning process. And if this is the case, we'd expect these cues to engage processes in the striatum and the ventromedial prefrontal cortex, which in turn would modulate these responses, leading to the changes in pain. And so we searched during the anticipation which regions responded to cues and predicted the responses within these pain mediator regions. And we found that only 2 regions did indeed formally mediate these effects of expectancy on these regions, and that was the striatum and a more anterior portion of the VMPFC. So just to remind you again, the reinforcement learning literature suggests that the striatum responds to deviations between expectations and experience, whereas the ventromedial prefrontal cortex is thought to track the predictions in expected value computations. So this kind of gives us a model that we're extending now that suggests that a domain general system involved in evaluating predictive cues and generating value signals is important for shaping domain-specific responses, those responses to noxious heat within these nociceptive portions, which in turn shape subjective experience, how much pain you feel. So we're testing this in other modalities now. But this also raises an interesting question. So these reinforcement learning models suggest that the expected values of the cues should actually change over time as you have these prediction errors, right? So early in the task, when you hear the low pain cue, you should expect low pain, and the same is true for the high pain cue. But then as we introduce those medium heat trials, you should actually have prediction errors generate, and you should update your expectations. So early in learning, those medium heat trials would be worse than expected if it followed a low pain cue. But you should update your expectations so that by the end of the task, when you hear the low pain cue, you're expecting something midway between the low heat and the medium heat. And so if these kinds of prediction errors are leading to learning, we would expect smaller expectancy effects by the end of the task than we have at the beginning of the task. But what we found is that the cue effects on pain were consistent across time. So I'm going to have run on the x-axis and pain on the y-axis, and we're just looking at the medium heat trials. And you can see, it's a little hard to see here, but that the magnitude of the expectancy effect at the beginning of the task is exactly the same at the end of the task. And people come out of the task and they have no sense that these medium heat trials were occurring. So why didn't these expectancy violations cause learning? If we have these signals, why aren't people updating their expectations? Well, there's a couple of possibilities. First of all, we're measuring subjective reports. So most of these tasks are designed in the context of the things like Tor talked about, where you're making a choice. But in this case, people are making a verbal description of their pain as opposed to a binary choice between two outcomes. So in that, there might be very different processes going into one's self-report than these types of discriminative choices. Secondly, perhaps these individuals are paying different attention to the outcome. We actually found that people seem to pay less attention when they have low pain expectancy than high pain expectancy. So perhaps because of the reduced attention, the prediction errors aren't registering. They're just kind of biased by the cues. And finally, our participants were instructed about cue contingencies. And research in reward learning suggests that verbal instructions can actually modulate these signals. So I'm going to be focusing now on the relationship between instructions and learning. So as I said, usually those of us who study expectancy, we combine these factors to maximize expectations and also to provide a model that is relevant for the clinic. But so in our case, we gave instructions and we also gave them conditioning. But when we do this, we can't really separate out the role of that verbal instruction conscious expectancy from that associative learning portion. And Benedetti has introduced a really beautiful paradigm for being able to do this. So if you give instructions that contradict what's learned from feedback, you can try to actually separate out tease apart these two influences. So Benedetti gave people several days of drug conditioning, and then on the fifth day or so, they came in and they were given verbal information that they were going to have the opposite type of treatment. So if they were pre-treated with morphine, they were told, today you're getting a drug that actually is going to increase your pain. And then they give a placebo, and they can test if the placebo response looks more like the conditioning or more like the instruction of what to believe. And that tells you basically whether the placebo response is dependent more on the conditioning or the verbal instructions. And what they found is that placebo effects on hormones, cortisol and growth hormone, I believe, looked like the conditioning phase irrespective of the verbal information that was given, whereas placebo effects on pain and motor performance in Parkinson's disease reversed immediately with instruction, suggesting they were more dependent on these kind of higher order schemas or beliefs about the treatment. Now, this is great, but in the clinic, patients aren't really going to have their doctor tell them to expect the opposite thing of what they're trying to get out of their visit. So what we wanted to understand is how does truthful information influence learning and subsequent responses? So to examine this, we turn to reversal learning. Tor also alluded to this in the context of the avoidance paradigm, But reversal learning is pretty nice because basically it causes people to have to update their expectations and learn new outcomes throughout the task. So in the beginning of the study, I might have learned that when I roll a 2, I get the shock. But then suddenly when I see an outcome with a white dice, those might become more predictive of my outcomes. And we can go back and forth flexibly to actually make sure that we can gauge different learning processes over time. So for the rest of the talk, I'm going to be focusing on aversive learning using a mild, annoying, but not quite painful shock. We're just using a fear conditioning model because we know a lot about the neural mechanisms engaged in fear conditioning, and we wanted to try to develop a paradigm that didn't require us to ask about subjective pain, but we're currently looking at the next steps relating these types of mechanisms to pain in my lab. So we can look then at how expected value shifts over time. And it turns out there's been, again, a ton of studies in reward literature on these types of reversal learning. And reversal learning actually implicates the same corticostriatal circuits as just value learning in general, although there are some specifics in terms of reversals, which I won't get into. So through this type of approach, I'm going to be addressing these 2 points, how instructions and potentially, if there's time, self-generated expectations shape aversive learning. We'll probably just focus on point 2. So basically, as I said, in the reward literature, Brad Dahl and Michael Frank, as well as Jian Li, have looked at how information about the relationship between stimuli and rewarding outcomes shapes responses. And what they found is that the prefrontal cortex maintains instructions and it modulates learning in the striatum. So striatal prediction errors are no longer seen in some cases when individuals receive information about the outcome. And so we were interested in understanding how instructions modulate aversive learning. So we developed a Pavlovian aversive reversal learning task, and we were interested in effects in the striatum and OFC, as well as the amygdala, which is highly implicated in fear conditioning and learning about threatening events in the environment. We did between groups manipulation, in which one group was assigned to a group that received instructions about outcomes, and a second group went through the exact same paradigm, but only learned through feedback, so they weren't informed about the probabilities. So in the uninstructed group, it's a simple reversal learning task. So what we would expect their learning process to look like is just kind of gradually learning that they're getting shocked when they see this CS plus, and then gradually learning, oh, now this one's shocking me. And we had 3 reversals across the course of the task. So then we had, and we were using 30% reinforcement contingencies. A second group is informed about the original contingencies and the reversals. So in this case, we always tell them a little bit before we actually pair the shock with the new CS+, we tell them that the contingencies are going to reverse. And so this lets us look for processes that actually update with instructions versus pathways that really need to receive that feedback and show more gradual learning simply as a function of feedback, right? So basically, we have the uninstructed group that allows us to isolate pure feedback-driven learning. And then within the instructed group, we can model things either as a function of whether we're telling them that things have reversed or look for the same signals that we see in the uninstructed group. We measured skin conductance responses and bold responses to the presentation of the conditioned stimulus. And we're going to focus on responses just within the individuals who showed differential skin conductance prior to the first reversal. Effects are the same when we include everybody in the group, but we're just focusing on fitting the models to the learners. And what we find, so here we'll look at reversals as a function of instruction in the instructed group and feedback in the uninstructed group. And we find that both groups do indeed reverse their skin conductance responses on unreinforced trials as a function of the phase as things reverse. But reversals are larger when people are receiving instructions than when they're learning purely from feedback. If we zoom in on responses within the instructed group, what you can see is that skin conductance increases immediately when people are instructed that things have reversed. You see this each time. But we don't actually see any additional learning when we actually pair a shock with that new CS+. So there's no additional elevation in the skin conductance response. So then what we did is we fit learning models to the skin conductance responses in each group. So When we fit the model to the uninstructed group, we can isolate pure feedback-driven learning. And we can search for neural correlates of that pure uninstructed learning in both groups to test whether instructions influence feedback-driven learning. And then we can fit another model to the instructed group to isolate learning that updates with instructions. So those are the groups that actually were informed about information. So to do this, we modified a standard reinforcement learning model, and we added a new parameter that basically measures how much things reverse with instructions. So if you get, if that parameter is equal to 1, it means just flip the expected value of the two cues. Whereas if the parameter is equal to 0, then it means that each of the cues just keeps their same value and you continue to learn from experience. So the parameter basically is what happens when we tell you that you received instructions, whether you got the instructions at that time or not. So we fit that model to skin conductance responses in both groups. When we fit it to the uninstructed group, indeed, we find that it's basically 0. So there's no reversal at the time of instructions for the people who didn't have instructions. So that's like a good check of our model. And then when we fit it to the instructed group, we found that indeed, at the time that instructions are delivered, skin conductance responses pretty much and expected value pretty much reverse immediately. So we can take these and now look for correlates of our uninstructed and instructed value signals. And what we find is that this uninstructed signal is associated with bilateral, uninstructed expected value is associated with bilateral responses in the amygdala and the uninstructed group, but also in the instructed group. So we found that the amygdala, and we tested this a bunch of different ways, including without models, so I'm not going into that into my talk, but the task was also designed to just use experimental approaches. We find that the amygdala in the instructed group tracks uninstructed learning and doesn't show any updating with instructions. When we looked for suggesting that the amygdala learns from feedback irrespective of instruction. When we looked for responses to the signal that updated with instructions, what we found is that the bilateral ventral striatum and the ventromedial prefrontal cortex both updated immediately with instructions and then continued to learn from outcomes after that point throughout the task. And finally, we looked for which region responded to instructions and modulated downstream responses. So this portion of the left dorsolateral prefrontal cortex showed greater activity across every trial in the instructed group relative to the uninstructed group. And then we went back to the individuals within the instructed group and saw how much did they activate this region in response to instructions, which basically gives us a magnitude of how much did you sort of engage with those instructions, I guess, across individuals. And what we found is that those individuals who showed higher DLPFC activation in response to instructions also showed larger reversals in the striatum as well as the VMPFC or medial OFC. So this suggests that, similar to reward, aversive learning in the striatum and OFC update with instructions, and the reversals in these regions correlates with the prefrontal cortex response. However, uniquely, unlike reward, we found that the amygdala responds to feedback irrespective of instructed knowledge. So in the interest of time, I'm not going to go into our last study. I'll just briefly say, I'll show you I think I have like 3 minutes or something. I can do it quickly. So basically here we were interested. We took the same exact approach and asked, instead of giving instructions, what about people's own expectations? Do those also engage similar sort of higher order processes that can modulate learning? So in this case, we had a single reversal and a higher reinforcement rate. So we can again just look at the reversal. And we had half the subjects assigned to a group where they just experienced the outcomes, and another half that made expectancy ratings on every trial. So when they saw the cue, they were asked how likely it was that it would be followed by a shock. And quite surprisingly to us, what we found is that rating expectancy actually slowed learning in this case. So when you're making your own expectations, we find that you're much less likely to reverse responses upon the reversal. And this is at a 50% reinforcement rate. So it's pretty crazy to us that it takes so long for skin conductance differences to emerge. And likewise, that it takes a really long time for the conscious expectancies to reverse. We fit learning models to these data as well, and what we found is that indeed learning rates were slower in the group that was making expectancy ratings than the group that was learning purely from feedback. And in our fMRI study, we found that also the striatum showed interactions between the cue contingencies and group, such that in the passive group, you see strong responses prior to the reversal, whereas in the expectancy group, the striatum doesn't discriminate prior to reversal. And then you see that in the passive group, the striatum reverses responses entirely, whereas the expectancy group, who's learning more slowly, is finally showing the initial contingencies. So in summary, we find that expectancy ratings actually slow feedback-driven learning. They influence skin conductance. We actually found that expectancies fully mediated the cue effects on skin conductance. They reduce the responses to reversals, and they also reduce differential responses in the striatum. And we think this is because these ratings are sensitive to complex higher order cognition. Things like gambler's fallacy are going into the ratings. So people might not be paying attention to those basic contingencies. But again, this shows that this striatal learning mechanism is indeed sensitive to higher order factors likely coming from the prefrontal cortex. So in conclusion, I think that this demonstrates that expectancy can interact with conditioning and value learning in some cases, depending on the system. So we had dissociations in terms of the influence on striatum and VMPFC, whereas the amygdala learned simply from feedback. We really want to highlight that we think effects on subjective pain are likely to be very different from effects on arousal, and we're currently seeing dissociations between skin conductance and pain responses in similar types of tasks. And finally, I think this illustrates that you can actually get into really useful work by thinking about isolating the dynamic computations of these networks, and that this type of new there's a big trend in psychiatry to do computational psychiatry and try to understand how these dynamic interactions between brain networks can help discriminate between different psychological function. So with that, I just want to acknowledge Tor, with whom I did the original expectancy work on pain, and then Liz Phelps and Nathaniel Daw, who were my mentors at NYU, where I did the aversive learning studies. Thank you very much for your attention.